Okay, we're going to get going again here because we're sysadmins, and if you give us 5 minutes, we'll take an hour and a half and then bill you. So now we're going to talk about harnessing the virtual. There are bad ninja skills. So we're talking about ZFS Datasets. So datasets are a control point. And they come in two varieties: file systems, which is a traditional POSIX file system, and volumes, which is a raw data store available as a block and a character device. They are intended to be nested, and each dataset has associated properties which can be inherited by sub-file systems and a parent-child relationship. It's good inheritance. And it's all controlled by the ZFS command. Like I said, there's two commands. You're going to use the zpool command to deal with physical devices to create pools and manage them, and then you're going to deal with the ZFS command to create datasets and manage them. So the file system dataset is the most commonly used. It's used to create a new dataset. You use the command ZFS create and then the name of the dataset. The dataset names are paths starting with the name of the pool, followed by a dataset, and there may be datasets underneath that, very much like a directory structure. Everything starts with a slash, right? A full path in Unix starts with a slash. That slash denotes the root directory, subdirectory, on down. Same idea. Datasets which act as a holder to other datasets are what I like to call stubs, meaning you're not actually storing data in there. It's just like a control point. Like, for instance, the home directory on most Unix machines contains no data. It's just a place where you create home directories underneath it, right? That's what I would refer to as a stub. So if I say stub dataset, that's what I mean. And new datasets inherit certain properties from their parent dataset, known as inheritance, where appropriate. One such example would be mount point. So if you create a dataset called pool/home, and you create a dataset called pool/home/ben, it's actually going to pick up the same mount point and do the right thing. So dataset properties, and this is where most of the fun in ZFS comes from, is these dataset properties. So to get all properties, you'd use the command ZFS get all, and then the name of the dataset. Really ingenious, complicated naming structure here, isn't it? Even I can remember it. Set properties in a similar sort of way. ZFS set key equals whatever the value and the dataset name. And properties kind of come in three varieties. There are native read-only properties, such as used. You can't change the amount of used disk, at least not by changing the property. It's just informational. Then there are native read-write sort of properties, such as setting a quota, sharing via sys or NFS. And then there is actually a third type, which is user-defined properties. So if you ZFS set donuts equals glazed on a pool, you'll get a new custom property called donuts with the value of glazed. That's simple. You can do it. Now, why would you want to do that? There are examples like, say, you're creating a backup system, and you'd really think, it'd be nice if my ZFS dataset just knew when it was last backed up. You could actually create a last underscore backup equals some date. Fun things you can do like that. Or if you like donuts, you can do that too. So, the other type of dataset are ZVols, volume datasets, which we call ZVols. It's a very fascinating naming structure. These are block storage devices that look like regular sort of block devices. They're actually, you can find them in the device tree, as you would expect block and character devices to be, /dev/zvol. And then there's two directories there, DSK and RDSK, for the block device and the character device. And then followed by the dataset structure. It's very sort of easy to find them. ZVols are important for special applications which may require block storage. In some databases, that might be raw file storage of, in, say, an Oracle database or something like that, where you actually need raw file storage. Other places would be like iSCSI, where you're sharing out some block storage allocation. You use that here. And you can also use it, obviously, for creating non-ZFS file systems. You could create ext2 or ext3 or ext4 or ext27, like Rambo. You know, they just keep making them, and they never are very good. UFS or whatever on these. I shouldn't say that. 4 is never going to work as is, right? So that might be the end. But you can do all sorts of fun things to those. They can also be created sparse. The marketing terminology for sparse is thin provisioning. It's like an option that you would spend hundreds of thousands of dollars on for like NetApp to get thin provisioning. And all that means is that you get to lie about how big it is. You create a LUN that advertises itself as 100 terabytes, when in fact it's like a 10 gigabyte server. In fact, I actually did an interesting blog entry where I created a volume that I created a UFS file system on that was like a petabyte in size, and I did it on like a local like USB key. The thing is it created like 30 gigs of metadata when it created the file system, and it took like half a day to do, because UFS, you know, writes every so often in the cylinder groups. But you could do it. There's no real point, but you can do it. Now, where that's useful, where thin provision is very, very useful, is if you're going to create like in iSCSI, you do this all the time. Growing many file systems is very complicated to do, if not impossible. Okay, so if you're going to say create an iSCSI share for a Windows server, you may have trouble later on growing the file system that's on it. So what you do is you just create a thinly provisioned ZVol. You say it's 100 terabytes or something like that. You create the file system on it. And then you just make sure that when it starts to fill up your pool, you actually grow it. But that way, your client never has to actually grow the file system. It's always bigger than it needs to be. Okay? So, and ZVols are nice that they're handled via properties. They're handled in the same sort of way that we actually deal with regular file system data sets. So, cold coffee. So does the concept of data sets make sense? So now we're going to go ahead and play around with a couple here. So the fundamental command you'll use is ZFS list. This shows us all of the different data sets. Okay. Here we created a pool, so we have one default data set created for us called Scotty. Okay, and we can go into here and like touch files. We can create additional data sets with ZFS create. Let's say I want to create an area for some home directories. So I'll create Scotty home. Very nice and quick. Notice there's not a preceding slash. It is not a Unix path. Scotty, in this case, is the name of the pool, and that is the root, not slash. Right? This is a mistake a lot of people make all the time when they're just not thinking, and you just, you know, as a Unix guy, your pinky just wants to hit that, you know, leading slash. So do another ZFS list, and there's our structure. Now, I can go and get some properties. I'll get all on Scotty. And we can see all of our properties here. Let's just look at some of them here. So we can see the type is a file system data set. It was created on Tuesday, June 2nd at 2:57. That's very handy. You can use that in fun ways. We can see that the amount of disk used by this data set and its children is 135K. Available 214 megs. Referenced is the amount of disk that's actually referenced by this data set and its snapshots. So if you start creating snapshots, like say you create a data set and you write 100 gigs of data into it, and you take a snapshot. How much on disk space are you using? 100, right? Then you go and delete all that. Would they say 100 megs or 100 gigs? So you delete 100 gigs. So now you've deleted it. There's nothing in the data set. How much disk are you using? 100 gigs because the snapshot still exists. So now you go and you write another 100 gigs into that data set. How many are you using now? 200. Right? In that case, the amount of disk used would be 100 gigs, but the amount referenced would be 200. Now, as soon as you let that snapshot go, it dropped back down to 100 referenced. Right? That's very, very handy when you're doing a lot of snapshots. Right? You can have a lot of things kind of held up. So, if we look down a little bit more, you notice these here, you see the source is a dash, right? That simply means that this is not something you can control. This is informational, okay? We see here the compression ratio. If you have compression turned on, you can see an idea of what the compression ratio you're getting. In this case, nothing, 1 to 1. So, if we look down some of these properties now, if you look down them, quota, fairly self-explanatory, how much disk they can use before they stop, right? Reservation is like a quota, except the disk is already pre-allocated. So in a quota, you could end up actually using all the disk available in that pool, and even though the user's quota hasn't been hit, they can't write data, right? Their SOL. If you set the reservation, it will pre-allocate it. Good example of this would be like, say you want to make sure that the CEO's home directory never runs out of space, right? That's a case where you may not want to use a quota. You may in fact want to use a reservation because you don't want somebody to be able to steal away the CEO's because he's going to ruin your day, right? The director of engineering, screw him, let him run out. Record size. This is the equivalent of block size in other file systems. Go ahead. They go nice together. So you could set a reservation. If you set a reservation, you're not actually setting, they are independent. So if you set a reservation, you've set that amount of disk aside for the user. But if you haven't set a quota, it won't stop them when they exceed it. So you typically would use these two together. You can play around them a bit. Quota is the one you most commonly use because you want to make sure that all your users can only have like a 10 gigabyte quota. But you only have 100 gigabytes on the machine total, something like that. And these are actually nested down, which I'm going to show in just a second once we get through some of these properties. Yes, sir? 2:57. This is probably an hour ahead. I just installed this yesterday. I don't know what the date time is. Yeah. Yeah, I'm not. Let's see what time it thinks it is. It thinks it's 3:42. Pacific Daylight Time. You caught me. I installed this in my bathrobe Friday morning, going oh dear Lord, the internet's not going to work during my talk. And I didn't care about anything except for the fact that I could actually tell not to it. Don't get me started in what's wrong with VirtualBox. Except that it's awesome. While I'm on this stage, VirtualBox is awesome. I love it. So looking down through some of these, you notice the record size is not something you typically need to worry about. I don't go a lot into this, but I'll give you the quick explanation. ZFS uses a variable block size. So the default is 128K for that record size. What that means is that it will write, if you write, say, 1K file, it will use a 1K block. It will write 1K to disk. If you write an 8K file, it will write 8K. 64K, 64K. What if you write 256K? Well, it exceeds the record size, so it will take a 256K write and cut it in half and write two 128K, right? So it's a variable block size, and that's essentially the upper limit, at which point it starts chopping it up. The only time I see people really change this is with databases, because databases believe that the entire world occurs in 8K blocks, right? And a lot of times what will happen is even though it'll write out in 8K blocks, sometimes databases will assume that the file system is going to take, like, say, 64K writes and chop them up itself. So instead of being written out in 8K blocks, it just assumes it's got to get taken care of somewhere else up the chain. And you end up with these like odd performance problems, because file systems like ZFS go, oh, look, I can optimize. And the database is not expecting that, and things go bad. So some people in the database world will set that to 8K, so that basically, it acts like a normal file system. But in the real world, don't worry about it. It's nice, you don't waste disk. So if you write, like, say, if you're doing like a mail server and you're used to this idea of I need to set the block size really small so I'm not wasting or creating a file system full of just fragments, you don't need to worry about it here. The mount point is configurable. You just change the mount point to wherever you want it to go, and it will be inherited down. And we see some of the fun options like share NFS. Turn that on, and it's exported. Checksum. Checksumming is an automatic aspect of ZFS. I don't recommend you ever turn it off. I have done some performance testing where I wanted to see, if I really slammed on it hard and turned checksumming off, would it make it any faster? And it's totally negligible. So don't ever bother about turning it off. Compression, it's a fun one. Turn it on, and you get compression. Talked about this in my talk yesterday, if any of you were there. There are two primary types of compression. The default, if you just turn compression on, is LZJB, JB for Jeff Bonwick. It's fast, it's low overhead, gives you decent compression. You can also use gzip, and just like gzipping a file, you can use gzip1 for like fast compression, not great, or gzip9, which is really good compression but really slow. You can do that. If you're at home and you've got a fast processor, you might want to use gzip, just get a little bit more out of your disks. So compression's fairly straightforward. I did a whole ton of slides yesterday. You can pull up that presentation if you want to get more on that. A-time. It's probably the single most commonly turned off option of any file system. So we'll start with that one. ZFS set A-time equals off on Scotty. Go get our properties again. So everyone know what A-time does? Access time, aka useless disk writes. Useless. There's no purpose. Who gives a crap about A-time? Seriously. So that's the one we almost universally turn off. Notice that the source here is default, and now it's changed to local. That means that I've set it here. When we look at other data sets, you'll see somewhere it'll say inherited from, and it'll point up the stack. It means it's being inherited down. So looking at some more of this, devices. If it's turned on, it means that you are allowed to put devices on that data set. Turn it off, it means you can't. So that's sort of a security protection. Exec, that's a fun way to screw with somebody. You can't exec files. You may want to do that in home directories, though. You may not want people to be able to just download binaries and exec them in their home directories. So that's one you can turn off. Set UID, same sort of thing. Read only, fairly straightforward. It's off by default, but turn it on and people can. You have a data set in read-only mode. Zoned has to do with zones. Even when you deal with advanced stuff in zones, that one is handled automatically for you, so you never have to worry about it. But that does refer to zones. Solaris containers. Snapdir is a fun one. Notice it's currently hidden. We're going to look at that one more in a little bit. ACLs, that's one of the things we said I'm not going to talk about. ACLs are implemented in ZFS based on the NFS v4 model, which is brilliant and complicated. And good luck making sense out of it. That's one of those things you really need to read a book on how to do. It's so hard to explain. But if you're really into ACLs, go for it. Just so you know, ACLs I think are one of those things that are handy on the command line, but they really fit much better into a Windows world when you have checkboxes. And ACLs are very, very easy. When you do it on a command line with bit masks and things like that, it gets icky. And I don't like it. But, there you go. Can mount. That's a fun one to mess with people. whether or not it can be mounted. You can turn that off so it just won't be mounted. Extended attributes on by default. It's a number of extra things you can see about that in the manual. This one here called copies is a fun one. This is a feature what's known as ditto blocks. The thing is that there are certain cases where you create a ZPool with one device, right? The problem is what if something goes corrupt on that one device? There's no redundancy. There's nowhere to get it from. If it's corrupt, it's corrupt. If you set copies equals 2, when it actually writes files, it will write 2 copies of the file in different areas of the disk. Which means on, say, your laptop drive, if a block goes bad, you got another one. You can actually set copies to 3 or 4. Tremendous. You're thinking like, wow, that's a great way to waste a lot of disk space. But if you're on a laptop drive, and you can't mirror devices or something like that, you may want a little redundancy. And I will tell you that there are cases where I've created ZPools on, say, a RAID 5 hardware device, right, where I didn't, if something failed, I was kind of SOL and just had to assume that the RAID controller would deal with it properly. If I didn't trust it, I just bumped that up to 2, right? And wasting disk space on an EMC is not a sin, right? You're just making sure somebody else couldn't buy it, which is great. Looking at some more of these, version 4, that's an on-disk format thing. Don't worry about it. UTF-8 only. Normalization, or a lot of these we don't typically worry about. Case sensitivity. If you have Windows friends and you want to be sensitive, you want to cry. vScan assign I talked about yesterday. You actually can cause every I/O on ZFS to be checked by a virus scanner. Like, it's awesome. Except I run Solaris, so I don't really worry about viruses. But other people are stupid. NBMAND, that's some kind of NTFS. Maybe some of you know about that. It's like non-block demand, right? Whatever. It's a sys thing. Share SMB. SMB is Samba. SMB shares server message bus, right? That's essentially sys. Turn that on. Ref quota and ref reservation. These are 2 things that actually go back to what we were talking about before with reservations and quotas. Because like I said, the amount of disk used and the amount of disk referenced are different. So you can actually set a quota on the amount referenced. So what's nice is that if you set a quota of 15 gigs on a user and you create a bunch of snapshots and data changes, the size of the snapshots counts against the quota, which can confuse a lot of users. Especially we saw this at Joint when we started doing this early on. There would be people who would like, hey, I'm deleting files to clean up space, and I'm actually using more. This is kind of kooky. It's kind of like the Twilight Zone. Or just like, yeah. So we begged and pleaded Jeff Bonwick, and he made this for us, for a lot of us. Reference quotas, where you can actually put a quota on the reference. So above. So you may set a quota of 15 gigs on a user, but you want to allow them like an extra 10 gigs for snapshots. So you would set the reference quota higher, say 25 gigs. Okay, so you can set quotas on both referenced and used. Same for reservation. And then these 2 down here, these at the bottom, are fun for you can really hack on these. Some new ones. These are pretty new. Primary cache. You can specify what kind of data is from this data set is actually cached in memory. Primary cache would be the adaptive replacement cache, ARC. I know ARC, you're just like RC read cache. No, you're wrong. But it's easier to remember. So primary cache, you can specify whether all the data goes into the read cache or just metadata. So you can kind of pick and choose. Same with secondary cache is that L2 ARC. That would be the cache device that we created at the ZPool level. So you can actually specify that, say, on some given pool that has like all of my pirated movies that I don't actually own, I don't really want I don't want to waste my precious DRAM for that. So only put L2, only put metadata in DRAM cache, but I have a SSD cache device that I stole from my gamer buddy who stoned, and now I can put all the read cache on that secondary device. These last ones here at the bottom are fun if you want to really hack around, and this gives you an idea of some statistics used by snapshots, used by dataset, used by children. This is just more statistics, because those of us who love ZFS just love complaining about the need for statistics. We love statistics. Statistics. Okay? Datasets clear? Yes, sir.
One is, when you say dataset property, so when you do a list, it will come out as another list. Is that correct? When you say dataset property, you got to kind of obey. It doesn't show up on a list or not.
Well, I wasn't really going to get into this, but let me just show you real quick, because I'm actually kind of going slower than I thought. So if you just run ZFS with no arguments, you'll see all the different subcommands here. And believe it or not, we're working through all these slowly. And you notice on the get, there's actually a whole ton of options. It's very, very, very scriptable. You can specify how you get it back, just getting individual fields. Like I said with that time field, if you specify that to come back in like script happy format, it will actually return it to you in epoch seconds, which is awesome. So very configurable. But let's move on. Snapshots. Snapshots are awesome. And it's the natural benefit of ZFS's copy on write design. Creates a point-in-time copy of a data set. Pretty straightforward. It can be used for individual file recovery or full file system or full data set rollback. It applies to both file system datasets and volume datasets. It's a fundamental building block of advanced functionality. There's a lot of advanced things we do that are all dependent on that. And they're denoted by the @ symbol because it's not used enough in our culture. So we use it some more. And here's an example of creating one. ZFS snapshot, name the pool set, @ sign, and then the name. In this case, snapshot is named now because it's very creative. Snapshots consume no additional disk space until they start to diverge. Right? We talked about this before. So you all got that concept. So some hidden goodness. One of the most amazing things, and one of my favorite features, is that for file system datasets, you can go back to old snapshots in a hidden .zfs directory in the dataset root. So you can actually go back and pull individual files out. You don't have to do a full recovery. There is a vendor out there who has similar functionality that many of us love. But I can't mention them because I'll be sued and subpoenaed and killed. But you probably know who they are. Well, what, who, what, where? So, can be exposed by changing snapdir property, which is one of the properties you saw before. You notice that it was set, the snapdir was set to hidden. It means if you run an ls-al, you will not see it. You can change directory to it, and it's there. It's creepy. You can change that to visible, and then it will actually show up. That's handy if you want to be able to see it in the file manager or something like that. Within the snapshots directory, you can see all the snapshot names, and you can navigate snapshots to pull out data in the normal sorts of way. You can copy files out or sync data out, whatever. And it's read-only, of course. So a rollback would irreversibly revert to a data set of previous snapshot state. Okay? Common example would be to recover, say, your database data once it was hacked. And all the snapshots more current than the one that you roll back to are obviously destroyed. Right? If you create an hourly snapshot and you want to roll back, and it's 6 o'clock and you want to roll back to noon, when you roll back to noon, all those snapshots at 1, 2, 3, 4, 5, 6, o'clock, poof, gone. Okay? So we can take a snapshot and pull data out of it. We can roll back to a snapshot at some given point in time. And we can also clone it. So we can clone any given snapshot into a separate read-write data set. Clone acts like any normal data set but consumes no disk space, right, because of copy on write. And it can be used to, say, access old data for testing without disturbing the real data, or quickly replicating any application environment. This is something we do extensively at Joyent. Right? When we create a new virtual environment, we're actually just cloning a ZFS file system, which is why we can do it fast.
So snapshots will change, and snapshots evolve, whereas a clone is actually static.
So clone is, snapshots will never change, right? They're a point-in-time copy. So, and it's not, no. Because a snapshot is a point-in-time copy of what some volume looks like. That volume may continue to change, but the snapshot does not. You may create new snapshots. When you create a clone, you're creating of some given point in time. Anything else changing around it doesn't affect the clone. Okay? Now, the caveat here is that you're still dependent on the origin snapshot. Okay? There's a relationship between the clone and the snapshot. Therefore, there's another option which can be a little confusing initially called promotion, which allows you to promote a clone. Clone datasets maintain that relationship, right? So you can sever that relationship by promoting it to its own autonomous state. The caveat here, the trick is that when you do that, you're no longer dependent on that snapshot, which means you have to duplicate all that data. So the clone that was using no disk until you changed, the contents, now actually consume disk space. But it's autonomous. So here's an example of how you kind of put all that together, because it is kind of a big concept conceptually. So say via cron that you snapshot your database hourly. During the night, the database is hacked and damaged. It would never happen to you. It happens to somebody else. We understand. I'm not talking about you. I'm talking about your customers. So you want to get back into business but want to investigate more, right? Common situation. So what you could do is you could clone the snapshot of the database in a hacked state and then promote it so it's autonomous and then revert the original back to a point in time prior to the hack. Okay? You get that? So you take your snapshot that's busted, you clone it, and then you want to roll back. So you can't depend on that snapshot. So you promote that out to an autonomous state, and then you roll the original data back. So you could do this, and now you have a hacked copy of the data and a working copy of the data separately. And you're back in production, and you can take all the time and you want to go through all the bad data. Okay? So let's watch this. So here, we'll create some more data sets here. So there's the Rockwood clan. Okay, so I've got a bunch of directories, and we'll set some properties here. You notice currently that the amount of used is the same, so it's 28K. The amount available is 214 megs. I'm going to set a quota on all the home directories, say 100 meg. Okay, so you notice I just changed the quota for Scotty Home, and now everyone is capped to 100, right? And let's say that, like, my daughter doesn't really need that much, so I can even go modify her quota. Quota equals, say 10 megs, because I'm a mean dad. Oop. I'm going to blame it on the lights that are really bright. Okay, so you can see we messed around with some properties. And so now let's go ahead and create a snapshot. So I'm here in my home directory. I move a bunch of data in. This is a bunch of junk data. Okay. Actually, Remember I said before that there's that list snapshots feature on the pool? I'm actually going to modify that before I go on here so you can see all the snapshots. Otherwise, you have to specifically say you want to see datasets of type snapshot, which is no fun. So, okay. Okay, so here we go. So you notice I've got 1.5 megs worth of stuff in the Benar directory. And I'll go ahead and now snapshot this. ZFS, snapshot. Scotty, home, Benar at 001. Okay? Whatever you want to call the snapshot. ZFS list, and you can see I have the snapshot, and the snapshot is consuming no space. Okay? And I'm in this directory. So now I go and I'm mean, so I destroy shadow, and I write garbage into password if I redirect properly, because I'm just mean. Let's say this happens in the middle of the night and I don't know anything about it. You notice that the size of the snapshot has changed because what it was referencing has changed. Okay? But now I want to get back to that state. Some of the things that we can do with a snapshot, we can create another snapshot. I'll scroll back for fun. So now I've got 2 snapshots. And say I want to create a copy of one of these. Let me show you this first. So my password file is jacked, right? So one of the easiest ways to get that file back would be in that dataset to cd.zfs, right? Right? You don't see it there, but it is there. And under there, you see this snapshot directory. And in that snapshot directory, you see the names of the snapshots. And in those directories, we see all the data as it looked in that snapshot. So this first snapshot is before I messed up the file, right? So if I cat password, it's the way it's supposed to be. I created that other snapshot after I screwed up that file, right? So if I go down and look at the contents of the 002 snapshot, it's screwed up. So if I want to recover, I could say roll back to this 001 snapshot. Or if it was, say, just that one file, I could just copy it out to, Scotty home Benar, right? Just simple copy procedure. And the file's back to where it needs to be. This is really, really handy when users delete or screw up files in some way. It's really, really nice to be able to just go as an administrator and pull that one file back. If you've ever had to recover a single file from a tape backup for a customer, you know what I'm talking about. They're like, I deleted this one file. Could you please help me out? You're like, no, because it's going to be 2 hours of my morning. Screw you. You don't need it. But it's my son's picture of his baseball game. And you're like, oh, you shouldn't have told me that. And I'm running kind of long, actually. I know. It's awesome. So we'll move on to replication. So datasets can be sent and received. One of the other things you can do with snapshots, right? And you send them as a single stream, which means you can do some kind of cool, amazing things. Here's an example where I ZFS send some snapshot, standard notation, and pipe it to SSH, to some other destination where it is received. One of the cool things here is that because it creates a single stream, is that you can actually use this kind of like dump. You could actually dump this into a single file, or you could stream it into a tape system, or you could say pipe the data stream of that snapshot into something like an encryption algorithm that then passes it into a compression algorithm, then moves it across the wire and undoes all that stuff. something I've blogged quite a bit about. Now, this section I'm going to move through very quickly because I talked about it yesterday. But the short version is that we have sys, NFS, and iSCSI hooks in ZFS on each of the data sets. You simply turn the parameter on, and the right thing happens, assuming that the right server, the NFS server, the iSCSI target daemon implementation, and the sys server are actually installed. So you just turn it on, and it works. And I'm not doing a demo. So we already talked about record size earlier, how that kind of works, what it consumes. So we already kind of talked about that. ARC is the adaptive replacement cache, the ZFS read cache. It exists in physical memory, and it dynamically grows and shrinks. And it's very intelligent. It actually maintains 4 cache lists. Those are the most recently used MRU, the most frequently used MFU, and then it has 2 ghost lists, which are basically lists of what got removed from those 2 lists. So it knows what it's recently been asked for, what it's being asked for repeatedly, and what it was, and equivalent of those 2 lists of what is it being asked for that I actually kicked out. So it knows what it has, how often it's being asked for, and what it doesn't have but keeps getting asked for. So it's a very, very intelligent cache. And here's the fun part. It can consume up to 7/8 of physical memory. And remember, you are buying systems from Sun Microsystems today where 32 gig is like the standard. You're now buying systems that are 64 gigs and 128 gigs. I am anyway. I assume you are too. But that's where it's going. 7/8 of that is a lot of memory. But if you've been using Solaris for a while, you know that it will find creative ways to use your memory. There are a number of case stats which are handy and a number of tools that you can find with useful information. I'll point to this one. ARC Summary is a tool I wrote that will actually look at case stats from ARC to give you an idea of how efficiently it's being used. So we can introspect a lot of these things without being hardcore and going to dtrace. And if you want to get really hardcore, then go over to Max Bruning's talk, and he'll tell you how to do like brain surgery on Solaris while it's running. Prefetch is something I actually recently blogged about. You can read about it in depth. But basically, it feeds the ARC, the read cache, with blocks before you ask them. And so basically, you say, I need a block. It goes, tell you what, I'll get you 2. And you use both those blocks. It goes, tell you what, I'll get you 4. And then you use those 4 blocks, and it goes, you know what, I'm just going to start going out there and just grab tons of disk. And ultimately, you're fetching the data and putting it in ARC before you even ask for it. It can be turned off, but don't. The VDev Read-Ahead is a way of reading ahead on disk structures in order to pull things out, again, with a per VDev read-ahead cache. Not very exciting. Like I said, I just wrote a blog entry on prefetch and VDev Read-Ahead, so you can read that in detail. Cache flush. ZFS actually works better with cheap drives from Fries than it does with EMC symmetrics because of the fact that it's aware of things like caches. So it will go out, and when it writes a critical operation to a disk, it will actually tell it, like, please flush your cache. Fun things like that. These are things that can be turned on and off inside of ZFS. I don't recommend it. But if you are, say, using a gigantic EMC symmetrics that has a 1 gig read cache on the device, if ZFS tells it to flush every 5 seconds, that might not be real great. So you can turn it off, but unless you'll have an idea if you should turn it off. Transaction groups are an advanced concept that I don't have time to get into here, but like I said, ZFS has more in common with your SQL with the transactional database than it actually does with the file system. So everything's queued up into a transaction and eventually moved all down to disk. And so if you look at IOStat, which you shouldn't do, if you use IOStat, you'll see things look kind of bursty. When you do like a benchmark or something like that, you notice it doesn't constantly write out. Right? If you do a sequential write to disk, you will not see constant access to disk in IOStat. You will see no I/O for about 30 seconds, and then splat. It'll do this massive burst write, and then it'll be quiet for 30 seconds. That's a transaction group being flushed. I did a whole presentation on this at the Storage Summit, and you can see more about that in detail. But I want you to understand what a transaction group is, and that if you see what looks like bursty activity, it's not a broken configuration. It's ZFS doing its job. And monitoring I/O, that's something I talk about in other talks a lot. But FSStat, if you always have used IOStat, please understand there is a tool called FSStat, which can show you VFS layer, the virtual file system layer statistics, and they'll give you an idea what's going in and out of ZFS, not necessarily up and down to the disks, but going in and out in terms of real requests. There is a write throttle. You can turn it off, but don't. And the intent log, how much rope are you going to give me here? You can't? So, and hybrid pools are something we talked about too with those cache devices and log devices. So that's kind of how you can use SSDs to expand your pools. So, given that I went long, like I said, you have my email address. Please feel free to email me if you have any questions. I've written about every single one of these topics in depth in my blog. So if you just search Google for any individual topic, you'll get a very long description of it. But I hope that particularly talking about some of the properties and the way pools are configured will give you a very good basis for really digging deeper into it. So are there any immediate questions that are quick? I know, it was like just kind of driving along at 35 miles an hour and then hitting a wall, wasn't it? I'm sorry.
My name is Rudolf. I'm working a lot of virtualization, and my question is if there is any way how to say to the ZFS file system to clean what was actually used for writes. Because one of the features of copy overrides that after I install the system, I have some chunk of the virtual hard disk which is basically not occupied by the used data, but it's still not zero.
I don't quite understand, but let's talk about this in back, and I'll get that one. Nick, you want to come up and start setting up? So thank you, everyone. Sorry it was so abrupt.